May 18th, 1945, Royal Aircraft Establishment, Farnborough, England. The massive hangar doors groaned open as a team of British engineers wheeled in what appeared to be an alien craft from another world. The sleek, swept-wing aircraft bore German markings and a design unlike anything they had ever encountered. This was a Messerschmitt Me-26AU, the world's first operational jet fighter, and it had just been captured intact from a Luftwaffe airfield in the final days of the war. Captain Eric Brown, the Royal Navy's chief test pilot and one of Britain's most experienced aviators, walked slowly around the aircraft with a mixture of fascination and concern. He had flown nearly every Allied fighter in service, but nothing had prepared him for what he was seeing. The Me-262 represented a quantum leap in aviation technology that would fundamentally challenge everything the British thought they knew about aircraft design and performance. What these engineers discovered over the following weeks would send shockwaves through the British aviation establishment and force them to confront an uncomfortable truth. Despite Britain's pioneering work in jet propulsion and their apparent technological superiority over Nazi Germany, the Germans had achieved something that seemed impossible. They had created a production jet engine that was not only more advanced than anything the British possessed, but operated on principles so sophisticated that British engineers struggled to understand how such performance was even achievable. The story of what happened when Britain's finest aeronautical minds examined the Me-262's revolutionary power plant is not merely a tale of wartime technological competition. It is a narrative of scientific humility in the face of unexpected innovation, of established experts discovering that their fundamental assumptions about jet engine design were incomplete, and of one captured aircraft that would reshape the entire future of aviation. The mathematics of jet propulsion were being rewritten not in British laboratories, but in the engines of an enemy aircraft that had somehow achieved performance levels that defied conventional engineering wisdom. The British had invented the jet engine, had developed the world's first operational jet fighter in the Gloucester Meteor, and believed they understood the limits of what jet technology could accomplish. The Me-262 would prove that those limits existed only in their imagination. The path to that hangar at Farnborough began 4 years earlier in the skies over Germany, where a revolutionary aircraft was about to challenge every assumption Allied intelligence held about German technological capabilities. April 18th, 1941, Augsburg, Germany. The prototype that would become the Me-262 lifted off from the Messerschmitt factory airfield, but this first flight revealed none of the revolutionary potential that would later terrorize Allied bomber crews. The aircraft flew with a conventional Junkers Jumo 210 piston engine, its jet engine nacelles empty, waiting for power plants that existed only as experimental prototypes in distant laboratories. The development of what would become the world's first operational jet fighter had begun 2 years earlier in April 1939, when Messerschmitt received a contract to design an aircraft around the revolutionary turbojet engines being developed by various German manufacturers. The project proceeded with typical German thoroughness, but progress was painfully slow as engineers grappled with technologies that had never been attempted at operational scale. The heart of the revolutionary design lay in engines that were still theoretical concepts when the aircraft's development began. Dr. Anselm Franz at Junkers had been working on a radical new approach to jet propulsion that differed fundamentally from the designs being pursued by British engineers. While Sir Frank Whittle and his team had focused on centrifugal compressor designs that built upon existing supercharger technology, Franz had chosen a path that was simultaneously more conservative and more revolutionary. His Junkers Jumo 4 engine would feature an axial flow compressor, a design that allowed continuous, straight-through airflow rather than the radial expansion and compression used in centrifugal engines. This seemingly subtle difference would prove to have profound implications for performance, efficiency, and the future of jet propulsion. The axial flow concept offered theoretical advantages that were immediately apparent to German engineers. The straight-through airflow pattern allowed for higher compression ratios through multiple compressor stages, something that was extremely difficult to achieve with centrifugal designs. The axial configuration also produced a much smaller frontal area, reducing drag and allowing for better aerodynamic integration into the aircraft structure. But these advantages came at an enormous cost in complexity, manufacturing precision, and operational sensitivity. Franz and his team were attempting to create a production engine using principles that pushed the boundaries of 1940s materials science, manufacturing techniques, and engineering knowledge. What they achieved would represent one of the most remarkable technological accomplishments of the war, but it would also reveal the fundamental limitations that Germany faced as the conflict consumed the resources necessary for advanced development. July 18, 1942, the Me-262 prototype finally achieved its first jet-powered flight, 15 months after its initial takeoff with conventional engines. The delay reflected the immense challenges involved in developing operational turbojet engines from theoretical concepts. The Jumo 04 engines that powered this historic flight were crude prototypes that bore little resemblance to the production engines that would eventually power operational Me-262s. These early engines were hand-built using the finest materials available, with turbine blades forged from high-temperature alloys containing generous amounts of nickel and chromium. The performance was remarkable, but the engines required constant maintenance and could operate for only a few hours before requiring complete overhaul. Even in this primitive form, the Me-262's performance was extraordinary. The aircraft achieved speeds that were simply impossible for piston engine fighters, climbing rapidly to altitudes where conventional aircraft struggled to operate effectively. Test pilots reported that the sensation of jet-powered flight was unlike anything they had experienced, with smooth acceleration and the absence of the vibration and noise that characterized piston engines. But these early flights also revealed the fundamental challenge that would plague the Me-262 throughout its development and operational service. The jet engines were extraordinarily temperamental, requiring careful handling and constant attention from pilots who had spent their careers managing the predictable power delivery of conventional engines. The development program that followed represented a race against time, as German engineers attempted to transform experimental prototypes into reliable production aircraft, while the war situation steadily deteriorated around them. The challenges they faced were unprecedented in aviation history. They were developing not just a new aircraft, but an entirely new category of propulsion system, using materials that were increasingly scarce as the Allied blockade tightened around Germany. The sophisticated alloys required for turbine blades to withstand the extreme temperatures and stresses of jet engine operation contained strategic materials that Germany could not obtain in sufficient quantities. Nickel and chromium, essential for high-temperature strength, were virtually unavailable as German supply lines crumbled under Allied pressure. The material shortage crisis forced German engineers to develop solutions that were both ingenious and ultimately problematic. Production versions of the Jumo 04, designated as the 04B model, were dramatically simplified compared to the original prototypes. Turbine blades were redesigned using hollow construction to reduce material requirements while attempting to maintain structural integrity. Combustion chambers were simplified to use less strategic metals. Manufacturing processes were streamlined to accommodate less skilled workers and reduced quality control. The result was an engine that retained the basic performance advantages of the original design while becoming fundamentally unreliable and short-lived. These production engines typically operated for only 10 to 25 hours before requiring complete overhaul or replacement, with some failing after as little as 10 hours of operation. The turbine blades, manufactured from inferior materials, would gradually stretch or creep under the extreme operating conditions, eventually leading to catastrophic failure. Pilots learned to treat their engines with extreme care, avoiding rapid throttle movements that could cause the engine to flame out or explode from excessive fuel injection into the combustion chambers before adequate airflow could match the increased fuel flow. Despite these limitations, the Me-262 remained a formidable weapon that represented a technological advantage of several years over anything the Allies possessed or had plans to develop. The operational deployment of the Me-262 beginning in 1944 created a crisis of confidence among Allied air commanders who suddenly found themselves facing an enemy aircraft that could attack their formations and escape before their escorts could respond. The Me-262's speed advantage was so overwhelming that conventional interception tactics became obsolete. Allied fighter pilots discovered that their aircraft simply could not catch the German jets in level flight, leaving bomber formations vulnerable to attack by an enemy that seemed to operate with impunity. The psychological impact was as significant as the tactical challenge, as Allied aircrews realized they were facing technology that made their own aircraft appear obsolete. March 18, 1945, a formation of Me-262s tore into a United States bomber formation, demonstrating the devastating potential of jet-powered fighters when properly employed. In a single engagement, the German jets destroyed 12 bombers while losing only 3 aircraft, a kill ratio that would have been impossible for conventional fighters facing similar odds. The Me-262's heavy armament of 4 30mm cannons could destroy bombers with just a few hits, while its speed allowed it to attack and escape before fighter escorts could respond effectively. This engagement and others like it proved that the Me-262 represented a fundamental shift in aerial combat that threatened to neutralize the Allied bombing campaign that was crucial to victory in Europe. But the Me-262's operational service also revealed critical vulnerabilities that Allied pilots quickly learned to exploit. The jet engine's slow throttle response made the aircraft extremely vulnerable during takeoff and landing phases, when pilots could not quickly accelerate to escape attacking fighters. Allied commanders ordered their pilots to patrol near known Me-262 airfields, attacking the jets when they were most defenseless. The tactic proved devastatingly effective, with numerous Me-262s destroyed while attempting to take off or land rather than in air-to-air combat. The Luftwaffe attempted to counter these tactics by installing extensive anti-aircraft defences around jet airfields and providing fighter cover during the most vulnerable phases of flight. But the fundamental vulnerability remained. As the war neared its end, Allied intelligence teams began systematic efforts to capture German jet technology before it could be destroyed by retreating forces. Operationed by Colonel Lusty, Command Harold Watson and his team, known as ERs, represented one Watson's whiz of the most comprehensive technology transfer operations in military history. The teams collected not only complete aircraft and engines, but also technical documentation, manufacturing equipment, spare parts, and even German engineers and technicians who had developed the technology. The scope of the operation reflected Allied recognition that German jet technology represented a prize of immense strategic value that could accelerate their own development programs by years or decades. The systematic capture of German jet technology revealed the extent to which Allied intelligence had underestimated German engineering capabilities throughout the war. By the time Allied teams reached German facilities in April and May 1945, they discovered production lines, research facilities, and stockpiles of equipment that demonstrated a level of technological sophistication that challenged fundamental assumptions about German industrial capacity. The Messerschmitt factories alone contained hundreds of completed and partially assembled Me-262 airframes, while Junkers facilities housed thousands of jet engines in various stages of completion. More disturbing still was the discovery that German engineers had developed production techniques and design solutions that were years ahead of Allied capabilities, achieved despite severe material shortages and constant bombing of manufacturing facilities. The intelligence teams found that German jet development had proceeded along multiple parallel tracks, with various manufacturers competing to develop different approaches to turbojet propulsion. The Junkers Jumo J04 represented only one solution among several, with other companies developing alternative designs that offered different advantages and limitations. BMW had created the Doro 3 engine using a different approach to axial compression, while Heinkel had pursued designs that emphasized reliability over ultimate performance. The diversity of approaches revealed that German jet development was not the product of a single breakthrough, but represented a systematic exploration of jet propulsion principles that had been underway for years before the war began. Captain Eric Brown's initial examination of the captured Me 262 at Farnborough focused on understanding how the aircraft achieved performance levels that seemed impossible based on British calculations of jet engine efficiency and power output. The Gloucester Meteor, Britain's operational jet fighter, was powered by Rolls-Royce Welland engines that produced comparable thrust to the German Jumo 04, yet the Me 262 demonstrated significantly superior speed and climb performance. Brown's flight testing revealed that the difference lay not just in engine power, but in fundamental design philosophy that prioritized aerodynamic efficiency over conventional handling characteristics. The Me 262's swept wing configuration, initially adopted primarily to address center of gravity issues caused by the heavy jet engines, proved to have unexpected advantages for high-speed flight that British designers had not anticipated. The swept wings delayed the onset of compressibility effects that limited the speed of straight-wing aircraft, allowing the Me 262 to operate efficiently at speeds where conventional fighters experienced severe control problems. British engineers discovered that the Germans had stumbled upon design principles that would become fundamental to high-speed flight, achieved through practical experimentation rather than theoretical understanding of transonic aerodynamics. The detailed examination of the Jumo 04 engines revealed engineering solutions that challenged British assumptions about jet engine design and manufacturing. British engineers had chosen centrifugal compressor designs for their jet engines because the technology was proven, reliable, and built upon existing supercharger expertise. Developed during the war, the centrifugal approach allowed British manufacturers to produce operational engines quickly using familiar manufacturing techniques and materials. Frank Whittle's original designs had demonstrated that centrifugal compression could produce sufficient power for practical jet aircraft, leading British engineers to conclude that this represented the optimal approach to jet propulsion. The German axial flow design represented a fundamentally different philosophy that prioritized ultimate performance over immediate practicality. The Jumo 04's 8-stage axial compressor achieved compression ratios that were impossible with centrifugal designs of comparable size, explaining why the Me 262 could achieve superior performance despite using engines with similar thrust ratings to British jets. The axial configuration also produced a much smaller frontal area, allowing for better aerodynamic integration and reduced drag. British engineers realized that while their centrifugal engines were adequate for immediate operational needs, the German approach offered superior potential for future development. The examination revealed that German engineers had solved fundamental problems in axial compressor design that British researchers had considered prohibitively difficult. The challenge of maintaining stable airflow through multiple compressor stages while preventing destructive vibrations had been addressed through blade design and spacing techniques that represented years of experimental development. The combustion chamber design incorporated features that ensured complete fuel burning while minimizing pressure losses, achieved through configurations that British engineers had not considered. Most significantly, the integration of the compressor, combustor, and turbine sections demonstrated understanding of internal aerodynamics that exceeded British knowledge in several critical areas. But the detailed analysis also revealed the fundamental compromises that German engineers had. been forced to accept due to material limitations. The production Jumo-04 engines used turbine blade alloys that were clearly inadequate for the operating temperatures and stresses involved, resulting in rapid deterioration and frequent failures. British metallurgists examining the German blades found that they contained virtually no strategic alloying elements, relying instead on clever design features and reduced operating temperatures to achieve minimal acceptable service life. The hollow blade construction, while innovative, created stress concentrations that contributed to premature failure under operational conditions. The combustion chambers revealed similar compromises, with simplified designs that sacrificed efficiency and durability for ease of manufacture using available materials. German engineers had developed welding and fabrication techniques that allowed rapid production of combustor components, but these techniques produced joints and seams that were vulnerable to thermal stress and oxidation. The overall engine construction showed evidence of systematic material substitution, with components that should have used high-temperature alloys manufactured from ordinary steel with protective coatings that provided temporary protection at the cost of long-term reliability. British engineers conducting the examination found themselves facing an uncomfortable realization. The German engines were simultaneously superior and inferior to British designs, achieving better performance through advanced design principles while suffering from fundamental reliability problems due to material limitations. The axial flow compressor design was clearly superior to centrifugal approaches for high-performance applications, but German engineers had been unable to fully exploit this advantage due to manufacturing constraints imposed by wartime conditions. The examination revealed that Germany had developed the theoretical and practical knowledge necessary for advanced jet engines, but lacked the industrial capacity to fully implement these advances. The implications extended far beyond immediate technical considerations. British engineers realised that their own jet engine had been constrained by conservative development, hairy design choices that prioritised proven approaches over optimal performance. While the centrifugal compressor designs had allowed rapid development of operational engines, they represented a technological dead end that would limit future advancement. The German axial flow approach, despite its current limitations, offered a clear path toward higher performance engines that could power the next generation of military and civilian aircraft. The testing program at Farnborough focused on understanding not just how the German engines worked, but why they worked better than British calculations suggested they should. The Jumo-04's performance curves revealed operating characteristics that differed significantly from British engine designs, with power delivery and efficiency patterns that challenged existing theoretical models. British engineers discovered that their understanding of compressor aerodynamics was incomplete, particularly regarding the complex interactions between multiple compressor stages operating at different pressure ratios and flow conditions. The examination of manufacturing techniques revealed another area where German approaches differed fundamentally from British methods. The Jumo-04 production lines utilised simplified assembly processes that allowed rapid construction using less skilled workers, but these processes produced engines with built-in limitations that became apparent only after extended operation. German engineers had developed quality control procedures that ensured engines would operate acceptably for their intended service life, but made no provision for long-term reliability or overhaul capability. British manufacturers had chosen approaches that emphasised durability and maintainability, producing engines that could operate for hundreds of hours between overhauls, but required more sophisticated manufacturing techniques and higher-grade materials. The German approach produced engines that were essentially disposable, designed to operate effectively for their expected service life before being discarded and replaced. This philosophy reflected both the desperate circumstances of wartime production and a fundamental difference in engineering priorities that British designers found difficult to accept. The systematic comparison of British and German jet engine approaches revealed that both sides had made reasonable choices given their circumstances and priorities, but that the German solutions offered superior potential for future development despite their current limitations. British engineers began to understand that the path forward in jet propulsion would require adopting German design principles while applying British manufacturing standards and material science to achieve both high performance and acceptable reliability. The captured Me-262 aircraft and engines represented more than just examples of German engineering capability. They provided a roadmap for future development that would fundamentally reshape British approaches to jet propulsion and high-speed flight. The examination process revealed gaps in British knowledge that had not been apparent when comparing their own designs to theoretical possibilities, forcing a comprehensive re-evaluation of development priorities and technical approaches that would influence aviation development for decades to come. The comprehensive analysis conducted by British engineers revealed that the German achievement represented more than just superior design principles. It demonstrated a fundamental difference in how the two nations had approached the challenge of jet propulsion development. British engineers had pursued incremental advancement, building upon proven technologies and established manufacturing practices to create reliable, serviceable engines. The Germans had pursued revolutionary advancement, accepting enormous risks and sacrificing immediate reliability to achieve performance breakthroughs that redefined what was possible in aviation. The detailed examination of Jumo 04 internal components revealed manufacturing innovations that British engineers had not considered necessary or desirable. The German approach to turbine blade cooling utilized internal air passages that were formed during the casting process, creating complex internal geometries that improved heat dissipation while reducing material requirements. British turbine blades relied on solid construction and superior alloys to withstand operating temperatures, an approach that produced more durable components but required strategic materials that Germany could not obtain. The combustion chamber design incorporated features that demonstrated sophisticated understanding of high-temperature gas dynamics and fuel injection principles. German engineers had developed fuel nozzle configurations that achieved complete combustion while minimizing pressure losses and temperature variations across the combustor exit. The chamber walls featured cooling air passages and thermal barrier configurations that protected the structural components while maintaining combustion efficiency. British engineers found that their own combustor designs, while adequate for current performance levels, lacked the thermal management sophistication necessary for higher temperature operation. Captain Brown's flight testing program revealed performance characteristics that challenged British understanding of jet aircraft handling and operational procedures. The Me-262 demonstrated flight envelope capabilities that extended well beyond anything British pilots had experienced with their own jet aircraft. At high altitude, the German fighter could sustain speeds and climb rates that made conventional interception tactics obsolete. The aircraft's ability to accelerate through speed, ranges where British jets experienced severe control problems, indicated aerodynamic design principles that British engineers had not fully understood. The swept wing configuration produced handling characteristics that were initially unfamiliar to Allied pilots trained on conventional straight-wing aircraft. The Me-262 exhibited different stall characteristics, requiring modified approach procedures and landing techniques that reflected the fundamental aerodynamic differences introduced by wing sweep. British test pilots discovered that the aircraft's high-speed handling was superior to their own designs, but low-speed characteristics required careful attention to avoid dangerous flight conditions. Engine operation procedures revealed the complexity involved in managing the temperamental Jumo 04 power plants. German pilot training manuals, captured along with the aircraft, detailed elaborate engine management procedures that were necessary to prevent catastrophic failures during normal operation. Throttle advancement required gradual, carefully timed inputs to prevent flameouts or temperature excursions that could destroy the engine within seconds. British pilots found that their own jet engines, while less powerful, were far more forgiving of operational mistakes and required less sophisticated pilot technique. The fuel system design incorporated features that reflected German understanding of jet engine fuel requirements and consumption patterns. The Me 262 carried substantially more fuel than comparable British aircraft, but the Jumo Caesar 04 engines consumed fuel at rates that limited operational radius despite the larger capacity. British engineers discovered that German fuel system designers had anticipated the high consumption rates and designed storage and distribution systems that maximised available fuel while maintaining proper centre of gravity control throughout the flight envelope. The electrical and control systems revealed another area where German approaches differed significantly from British practices. The Me 262 incorporated engine monitoring instruments that provided detailed information about turbine temperatures, fuel flow rates, and compressor performance parameters that allowed pilots to optimize engine operation for maximum efficiency and reliability. British jet aircraft relied on simpler instrumentation that provided basic operational information but lacked the sophisticated monitoring capability necessary for managing temperamental engines. The structural analysis revealed that German engineers had developed construction techniques specifically adapted to the unique requirements of jet aircraft. The fuselage design incorporated reinforcement patterns that distributed the loads imposed by jet engine installation and operation, while the wing structure utilized construction methods that accommodated the sweep angle while maintaining adequate strength and stiffness. British engineers found that their own structural approaches developed for conventional aircraft were inadequate for the higher speeds and different load patterns associated with jet-powered flight. The landing gear system demonstrated German understanding of the operational requirements imposed by jet aircraft performance characteristics. The tricycle configuration provided superior ground handling and directional control compared to the conventional tail-wheel arrangements used on most contemporary aircraft. The gear design incorporated features that accommodated the higher landing speeds and different approach angles required for safe jet aircraft operation. British engineers realised that their own landing gear designs would require significant modification to handle the performance characteristics of advanced jet fighters. The armament installation revealed innovative approaches to integrating heavy weapons into high-speed aircraft structures. The Me 262's four 30mm cannons were mounted in the nose section using a configuration that minimized aerodynamic interference while providing devastating firepower against bomber targets. The ammunition storage and feed systems were designed to function reliably under the high G-forces and vibration levels associated with jet-powered flight. British fighters typically carried lighter armament that was adequate for fighter versus fighter combat, but lacked the destructive power necessary for effective bomber interception. The examination of German technical documentation, captured along with the aircraft, revealed the systematic approach that had been applied to jet aircraft development. Engineering reports detailed extensive wind tunnel testing, structural analysis, and performance optimization studies that demonstrated sophisticated understanding of high-speed aerodynamics and jet propulsion principles. British engineers found that German research had explored areas that their own programs had not yet addressed, including transonic flight characteristics, compressibility effects, and engine airframe integration challenges. The manufacturing documentation revealed production techniques that achieved remarkable efficiency despite wartime material shortages and bombing disruptions. German factories had developed assembly line procedures that allowed rapid construction of complex aircraft using simplified tooling and reduced skilled labour forces. The production drawings showed systematic design simplification that eliminated unnecessary complexity while maintaining essential performance characteristics. British manufacturers had pursued different approaches that emphasized precision construction and long-term durability over rapid production rates. The spare parts inventory captured with the aircraft revealed the logistical challenges involved in maintaining jet aircraft under operational conditions. German supply systems had been designed to accommodate the high failure rates and short service lives of jet engines, with extensive stockpiles of replacement components and rapid overhaul procedures. British logistics officers, examining the German maintenance procedures, realised that their own support systems would require fundamental restructuring to handle the demands of operational jet aircraft. The pilot training materials provided insights into the specialised knowledge required to operate jet aircraft safely and effectively. German flight manuals detailed procedures for managing jet engines that were far more complex than anything required for conventional aircraft. Pilots had to understand compressor stall characteristics, thermal limitations, and fuel management procedures that reflected the sophisticated nature of jet propulsion systems. British pilot training programs would require extensive modification to prepare aircrew for the demands of jet aircraft operation. The strategic implications of the German achievement extended far beyond immediate technical considerations. British intelligence analysts realised that Germany had developed jet technology that was years ahead of Allied capabilities, achieved despite severe resource limitations and constant military pressure. The systematic examination of captured technology revealed that German engineers had solved fundamental problems that British researchers had not yet fully understood, creating a technological advantage that could have altered the course of the war if deployed earlier and in greater numbers. The examination process forced British engineers to confront the reality that their conservative approach to jet development, while successful in producing operational aircraft, had limited their advancement to incremental improvements rather than revolutionary breakthroughs. The German willingness to accept enormous technical risks and operational limitations had enabled them to achieve performance levels that British engineers had considered impossible with current technology. This realization would fundamentally reshape British approaches to advanced technology development in the post-war period. The captured Me-262 represented more than just an advanced enemy aircraft. It provided tangible proof that technological superiority could be achieved through innovative engineering approaches that challenged conventional wisdom and accepted short-term limitations to achieve long-term advantages. The British examination revealed that their own expertise, while considerable, had been constrained by assumptions and limitations that were not inherent to the technology itself, but reflected conservative development philosophies that prioritized reliability over breakthrough performance. The psychological impact of these discoveries rippled through the British aviation establishment with devastating effect. Engineers who had spent decades developing what they believed represented the pinnacle of propulsion technology suddenly found themselves examining evidence that their fundamental approaches were outdated before they had even reached full production. The Rolls-Royce Welland engines powering the Gloucester Meteor, once considered marvels of engineering achievement, now appeared primitive when compared to the sophisticated axial flow architecture of the Jumo 004. British confidence in their technological superiority, built upon years of successful wartime innovation, crumbled as they realised that German engineers had been pursuing solutions that were years ahead of anything in British development programmes. Dr. Stanley Hooker, chief engineer at Rolls-Royce and one of Britain's most respected propulsion experts, visited Farnborough in June 1945 to personally examine the captured engines. His reaction, documented in classified reports that would remain secret for decades, revealed the profound shock experienced by British technical leadership. Hooker had expected to find crude, unreliable engines that achieved performance through brute force rather than engineering sophistication. Instead, he discovered power plants that demonstrated theoretical understanding and practical implementation of jet propulsion principles that exceeded British knowledge in several critical areas. The axial compressor design alone represented advances that Rolls-Royce had considered impossible to achieve in production engines. The detailed metallurgical analysis conducted by British materials scientists revealed both the brilliance and desperation that characterized German engineering during the final years of the war. Laboratory examination of turbine blade samples showed that German metallurgists had developed innovative heat treatment processes that extracted maximum performance from inferior materials. The blade microstructures revealed sophisticated understanding of grain boundary control, precipitation hardening, and thermal stress management that British scientists had not yet mastered. Yet these same blades contained virtually none of the strategic alloying elements that British engineers considered essential for high-temperature operation. The combustion chambers demonstrated similar contradictions between advanced design principles and compromised execution. German engineers had developed combustor configurations that achieved near-perfect fuel distribution and mixing characteristics, creating temperature patterns that maximized power output while minimizing thermal stress on surrounding components. The fuel injection systems incorporated features that British designers had not considered, including variable geometry nozzles that adapted to different operating conditions and staged injection patterns that optimized combustion efficiency across the entire power range. But these sophisticated systems were manufactured using materials and processes that could not sustain extended operation under the extreme conditions they were designed to handle. British test cell operations revealed performance characteristics that challenged existing theoretical models of jet engine operation. The Jumo 04 demonstrated fuel consumption patterns, power delivery curves, and operational envelopes that differed significantly from British engine designs. Most disturbing was the discovery that the German engines achieved their superior performance not through higher operating temperatures or pressures, but through more efficient utilization of available energy. The axial compressor design extracted more work from the airflow, while the combustion system burned fuel more completely, and the turbine section recovered more energy from the hot gases. British engineers realized that their own designs were wasting significant amounts of potential energy through inefficient internal aerodynamics. The manufacturing analysis revealed production techniques that challenged British assumptions about precision engineering and quality control. German factories had developed assembly procedures that produced acceptable engines using simplified tooling and reduced skilled labour, achieving production rates that British manufacturers had considered impossible. The key insight was that German engineers had designed their engines specifically for mass production, accepting certain performance limitations in exchange for manufacturing simplicity. British engines required precision machining, hand fitting, and skilled assembly that limited production rates, but produced more durable, maintainable power plants. The examination of German quality control procedures revealed a fundamentally different philosophy regarding engine reliability and service life. British manufacturers designed engines to operate for hundreds of hours between overhauls, requiring sophisticated materials and precision manufacturing to achieve extended service lives. German engineers had designed essentially disposable engines that operated effectively for their intended service life before being discarded and replaced. This approach allowed them to achieve high performance using inferior materials, but required massive production capacity to maintain operational fleets. Captain Brown's continued flight testing revealed operational characteristics that forced British pilots to reconsider their understanding of jet aircraft capabilities. The Me-262 demonstrated combat maneuvers and flight profiles that were impossible for conventional fighters, including high-speed climbs, steep diving attacks, and sustained high-altitude operations that redefined air combat tactics. The aircraft's ability to accelerate away from pursuing fighters made traditional interception methods obsolete, while its heavy armament could destroy bomber targets with brief firing passes that minimized exposure to defensive guns. But the flight testing also revealed fundamental limitations that British pilots could exploit. The jet engine's slow throttle response made the aircraft vulnerable during combat maneuvering that required rapid power changes. The engines were prone to flame out during negative G maneuvers, limiting the aircraft's defensive capabilities when under attack. Most critically, the engines required careful handling during all phases of flight. With operational procedures so complex that British pilots discovered that while error could result in catastrophic engine failure, the Me 262 was superior in straight-line performance. It was operationally fragile in ways that skilled opponents could exploit. The strategic analysis conducted by British intelligence officers revealed the broader implications of German jet technology for post-war military aviation. The performance advantages demonstrated by the Me 262 indicated that jet-powered fighters would dominate future air combat, making existing piston-engine aircraft obsolete within years rather than decades. The speed differential was so significant that conventional fighters could not effectively intercept jet aircraft, while jet fighters could attack and escape from any piston-powered opponent. British military planners realized that their entire fighter force would require replacement with jet-powered aircraft to maintain combat effectiveness. The bomber implications were equally profound. German jet fighters' ability to neutral demonstrated these Allied bombing campaigns through attacks that conventional escort fighters could not prevent. If Germany had deployed larger numbers of Me 262s earlier in the war, the strategic bombing offensive that contributed significantly to Allied victory might have become prohibitively expensive. British Bomber Command recognized that future bombing operations would require either jet-powered escort fighters or fundamental changes in tactics and targeting to remain effective against jet-equipped defenders. The examination of German research documentation revealed development programs that extended far beyond the Me 262 and Jumo 04. German engineers had been working on swept-wing designs, supersonic aerodynamics, and advanced jet engines that would have produced aircraft with performance capabilities exceeding anything the Allies had imagined possible. Wind tunnel models and design studies showed fighters capable of speeds approaching the sound barrier, bombers with intercontinental range, and reconnaissance aircraft that could operate at altitudes beyond the reach of any defensive systems. The systematic nature of German advanced research indicated that the Me 262 represented only the beginning of a technological revolution that could have transformed warfare. The propulsion research was particularly extensive, with multiple manufacturers developing different approaches to jet engine design. The Jumo 04 represented only one solution among several, with other German companies pursuing alternative configurations that offered different combinations of performance, reliability, and manufacturing requirements. BMW had developed the 003 engine using different compressor and turbine arrangements, while Heinkel had created designs that emphasized durability over ultimate performance. The diversity of approaches revealed that German jet development was not dependent on a single technological breakthrough, but represented systematic exploration of jet propulsion principles across multiple parallel development programs. The captured Me 262 that rolled into that Farnborough hangar in May 1945 represented more than just an advanced enemy aircraft. It was tangible proof that technological leadership could shift in ways that established powers never anticipated. British engineers had entered that examination confident in their pioneering role in jet propulsion, only to discover that their German counterparts had achieved breakthroughs that redefined what was possible. The axial flow engines that powered every modern airliner, the swept wings that characterize high-speed flight, and the manufacturing principles that enable mass production of complex aircraft all trace their origins to the revolutionary approaches captured in that single German fighter. The Me 262's legacy lives not in the aircraft itself, but in the humbling lesson it taught about the dangers of assuming that current knowledge represents ultimate truth. Sometimes the greatest discoveries come from those willing to challenge conventional wisdom and pursue solutions that others consider impossible.